Hello there. Today we're looking at what matters in on-policy reinforcement learning, a large-scale empirical study by Google Brain. On a high level, this paper investigates 5 different continuous control tasks, and they train agents with all the different choices that you can make basically on these continuous control tasks. So the different choices are like network width and height of the value and policy network, learning rate, type of loss function, regularization constants, and they train all of these agents and they try to parse out what works in general and what doesn't. And they have some surprising findings that number 7 will surprise you. Yeah. Okay, so that's the study on a high level. As always, if you like content like this, consider subscribing and sharing it out. That would be excellent. So they say that on-policy reinforcement learning has been successfully applied to many different continuous control tasks. While RL algorithms are often conceptually simple, their state-of-the-art implementations take numerous low and high-level design decisions that strongly affect the performance of the resulting agents. Those choices are usually not extensively discussed in the literature, leading to discrepancy between published descriptions of algorithms and their implementations. So the sort of things they mean here are the things that when you read the paper, the algorithm will be sort of described pretty well on the main idea. But then if you look at the code, there's a whole bunch of hacks there. Like on the Atari environment, you have to repeat certain actions. You have to introduce sticky actions. Then the question is, do you have like a random start, or do you always start at the exact same time? Therefore, the randomness of the level is not given. Then whether or not you normalize certain observations. But we've had these things even in supervised learning or NLP, things like this. We've had pre-processing. I remember the first ResNet paper that beat ImageNet to a significant degree over the last year's baseline. It was, we have this simple idea of the ResNet. And then they have an entire section where they go, and we do this normalization, we do this pre-processing, we do this and this and this and this and this. And there's an argument to be made for all of these choices, but often it's hard to disentangle if the choices of these pre-processing things or whatever the choices are matters, or if the idea in the paper matters. And it's also very hard to compare different things. So what they're doing here, so I would say this is not only a problem in RL, this is a problem generally. They say, as a step towards filling the gap, we implement over 50 such choices in a unified on-policy RL framework, allowing us to investigate their impact in a large-scale empirical study. So large-scale empirical study, it basically means grid search over these choices, kind of smart grid search. We train over 250,000 agents in 5 continuous control environments of different complexity and provide insights and practical recommendations for on-policy training of RL agents. So as far as I could figure out, the code and or the checkpoints of these 250,000 agents or the code of this unified on-policy RL framework is not available yet, and I don't know if it's going to be. But basically what they're doing is they're building one agent. So usually you have this agent environment dichotomy. Right here you get observation and reward, and here you give action. They build one single agent that has a lot of switches, that has a lot of like flags that you can say, okay, either do you want this loss or this loss? Cool. Do you want this regularization or this regularization? And if so, by how much, right? And so on. So I have this agent with lots and lots and lots of switches, over 50 of these choices that they implement right here. And they can basically turn each one on and off, and therefore they can investigate these algorithms. So let's jump over the most surprising finding, I can tell you the most surprising finding is that the policy initialization scheme matters significantly. Okay. That's what people maybe didn't know. What also matters a lot is the learning rate and things like the discount factor, but I think people in RL were already familiar with that. I find it also interesting what doesn't matter, namely most things seem to not really matter too much, but there might be other explanations for this. All right, so they say we consider the setting of on-policy reinforcement learning for continuous control. Now, this is where I have a bit of a problem right here, because the title is what matters in on-policy reinforcement learning. It's not what matters in on-policy reinforcement learning for continuous control. They do say in the abstract here, as you've already seen, in the last sentence, that they have continuous control environment, 5 continuous control environments. But yeah, I get it. You need to make the title a bit clickbaity, but the title overstates a bit what this paper says. This paper basically says what works in these particular 5 continuous control environments, right? So they vary a lot of things with respect to the agent, but they keep the environments relatively constant. And it's not 5 diverse environments. It's 5 MuJoCo continuous control environments that are very, very, very similar to each other in terms of their observation, in terms of how the world works, and so on. So consider this paper as an investigation in what works and doesn't work for these 5 and possibly for very relatively close environments. So that's I think my biggest trouble I have with this paper right here is sort of it overstates what it says in the title. But I mean, the investigation itself is done, I feel, very, very well. So they say they have a unified on-policy learning algorithm where they researched prior work, took popular code bases, made a list of commonly used choices, and then implemented everything into starting from the SeedRL code base. SeedRL is kind of a framework for distributed or for reinforcement learning in general. And they say whenever we were faced with implementation decisions that required us to take decisions that could not be clearly motivated or had alternative solutions, we further added such decisions as additional choices. So this, I feel, if I write research code, this is generally what I do, right? I write my research code, and whenever I come to a place where I'm like, should I use this or this? Should I use this optimizer or this optimizer? I simply make a flag, and then even if it's just one choice for now, right? Just make a flag and parameterize everything. And that's the thing here. They parameterize everything, but other than I would do now, then I would sort of sparsely explore the space of these parameters. Now they do a more dense observation or dense sampling of this space than me myself would do with limited resources. Of course, being Google, it is possible to do these kinds of things where you investigate all the choices. So they say here, difficulty of investigating choices. The primary goal of this paper is to understand how the different choices affect the final performance of an agent and derive recommendations for these choices. There are 2 key reasons why this is challenging. First, we're mainly interested in insights on choices for good hyperparameters. Yet, if all choices are sampled randomly, the performance is very bad and little training progress is made. So that means if you have all of these hyperparameters, then let's consider like a 3-dimensional hyperparameter space. Then there are combinations of hyperparameters that are very good, right? Here, maybe here. So there's this cube in here that's sort of very good, but the rest aren't really good. So if you just simply sample from anywhere in the space, like here, or here, or here, or here, or here, we will basically never get anything that works. You sort of have to hit the combination correctly. And that's a problem in 3 dimensions, but it's way more a problem in 50 plus dimensions like they have here. So they have to resort to a different strategy. They have to go and basically start out from a good configurations where they say they group these. We create groups of choices around thematic groups where we suspect interactions between different choices. For example, we group together all choices related to neural network architecture. We also include the learning rate in all of the groups, as we suspect it may interact with many other choices. Then in each experiment, we train a large number of models where we randomly sample the choices within the corresponding group. All other settings for choices not in the group are set to settings of a competitive base configuration that is close to the default PPO versus V2 configuration. Okay, so what they're doing basically is they're saying, now let's consider these. So these groups, you can now think of single dimensions in this space. So let's consider the space of groups. Let's say you have two different groups. One is the group of network architecture parameters, and the other one is the group of learning behavior, like learning rate and training algorithm parameter. What they're saying is, they're saying we know of a configuration right here that is good. This is PPO versus 2, version 2. And now what we're going to do is we're simply going to keep, in each experiment, we're going to, if we want to investigate the network architecture, let's say that's this axis, we're going to keep all the other groups the same as this default configuration, and only basically move this point to the left and to the right. And we're not going to move it up and down. We're going to keep the learning dynamic parameters of the other group, or all of the other groups, we're going to keep the same and only move it in the architecture parameter space. Now, of course, this is not just one parameter. Since they make these groups, this is a multi-parameter. So at each point here, you can imagine like a little subspace of the inner group, and they then sample from these. And that becomes much more feasible, right? So now maybe you have, let's say you have 10 groups of 5 parameters each. You can densely sample 5 parameters. Like that's sort of possible. You cannot densely sample 50, but you can densely sample 5. So what you would do is you would keep the other 45 constant. That would correspond to this dimension and all the other dimensions. And you would only vary within the group, which would correspond to this dimension. But now you see that the problem again, of course, is that you're always starting from this point, and you're basically only exploring along the axis of this group space, because you always keep the others constant. And that basically, to me, that means that these experiments are going to be heavily favored in terms of which of the algorithms is closest to this baseline, because if I go with this particular algorithm, I know that these parameters are the best for this particular algorithm. Where if I now use any other algorithm, these parameters might not be the best, and my only way of adjusting to that other algorithm is by individually moving here while keeping others constant. So I can basically only improve with it along one of the groups. I hope this makes sort of sense, that it feels like this experiment biases the results in favor of whatever choices are made in this baseline. So keep that in mind. Now, that being said, PPO, of course, is a very popular baseline, so it makes total sense to use that as a base to explore from. But it's not like they're doing an actual dense grid sampling of the space. They're doing a sparse sampling in the group space and then a dense sampling within each group. All right, so let's go into the experiments. The first thing they investigate are the policy losses. Now, this is a rather important topic, and that basically means how do you train the policy? And the choices here are, of course, PPO, like we saw, the proximal policy optimization, but there are also others, namely, for example, policy gradient. You might know that if you learn about reinforcement learning, you will inevitably learn about policy gradients, like the first thing you learn next to Q learning. And then V-trace is another sort of policy loss. V-trace is optimized for distributed reinforcement learning. And they have a bunch of others, and here they say the goal of this study is to better understand the importance of the policy loss function in the on-policy setting considered in this paper. The goal is not to provide a general statement that one of the losses is better than the others, as some of them were specifically designed for other settings. Now, of course, I agree with this statement. It's nice that they repeat it again right here. So all the results right here are just valid for these environments, or environments very similar to these. And you have to keep in mind that the baseline parameters are PPO V2, and they only ever vary one group from these baseline parameters. So that's why in this experiment, for example, it doesn't seem too surprising that the PPO loss, as you can see, outperforms in every single experiment here. Whereas the other losses underperform. So their recommendation is use the PPO policy loss, start with the clipping threshold to 0.25, but also try lower and higher values if possible. Because they have found, and they have more experiments. So in the appendix is full of these experiments, and you can go and look at them. But the general recommendation here for them is to use the PPO policy loss if you have these continuous control tasks, and that there is a strong influence of this clipping threshold that is in PPO. Second thing, network architecture. And that's basically you always have a value network and a policy network, and the question is how many layers, how deep, and so on should you make them. These things here are just MLPs. Since this is continuous control tasks, you don't learn from pixels as far as I understand it. You learn from the states or the sensors on these simulated robots. Now, you got this here. They say separate value and policy networks appear to lead to better performance on 4 out of the 5 environments. And further, regarding network sizes, the optimal width of the policy network depends on the complexity of the environment, and too low or too high values can cause significant drop in performance, while for the value function, there seems to be no downside in using wider networks. Moreover, on some environments, it is beneficial to make the value network wider than the policy one, e.g. on half cheetah. The best results are achieved with 16 to 32 units per layer, yada, 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 yada. This is a thing that sort of crystallizes out of this paper, because what you're doing is you have this one policy network and one value network. Like it's this dichotomy where the value network tries to estimate the reward, and the policy network tries to maximize the value. So you have two learning things here. You have this is learned, and this is learned. Now, there is a certain degree of interaction as the value network. Of course, the reward is dependent on your policy. So the value network sort of has to take into account the policy when it estimates the reward. But it seems to be that the policy network is the brittler one, and therefore more care has to be taken to optimize it, whereas the value network seems to be a bit of more robust to changes. And we've seen this already in that the loss choice for the policy seems to be quite important. And here also the network parameters for the policy seem to be the things you have to actually tune per environment. Whereas for the value, you can pretty much get any wide network will kind of do. Okay. So they say, as for activation functions, we observe that TAN-H activations perform best and ReLU perform worst, which is interesting, right? Because you would think that in other deep learning tasks, ReLUs have become pretty popular and usually outperform these other activation functions. But in this case, no. But this could also be due to other things, because again, they go from these default parameters, which, for example, do not have entropy regularization built in. And if you have a ReLU where it's basically an unbounded function, whereas the tan H is sort of a more bounded function. So that could be, there could be significant interactions here where they have split the groups, and then the choices might be reversed if in the other groups these parameters were different. But for now, apparently, tan H activations perform best. The interesting thing here is they say, interestingly, the initial policy appears to have a surprisingly high impact on the training performance. So this is how you initialize the policy network. Again, policy network appears to be the more brittle one and the one that you have to tune more. The key recipe appears to initialize the policy at the beginning of training so that the action distribution is centered around 0, regardless of the observation, and has a rather small standard deviation. This can be achieved by initializing the policy MLP with smaller weights in the last layer. So if you have this policy MLP as multiple layers, and then it needs to output an action distribution, right? So in these continuous control tasks, you basically for each of the joints you have to affect. So you have like a little walker here with 4 legs, and what's that? That's like 8 joints or something. So you have to tell this how much force it needs to apply to each of these joints, and as I understand it, that's usually given by the network outputting a mean and a standard deviation. I might be wrong here, but mean and a standard deviation for the distribution of action that's going to be applied here, and then this is sampled. From that distribution, the actual force is then sampled. Now they say you should initialize the network such that the mean here is 0 across or over your observations. And the way to do that is to simply initialize this last layer here with very small weights. So I think their recommendation is to initialize this by 100 times smaller weights than all the other layers. They say other choices appear to be less important. The scale of the last layer initialization matters much less for the value MLP, again, than for the policy MLP. Apart from the last layer scaling, network initialization does not matter too much. Yada, yada, yada. There appears to be no benefits if the standard deviation of the poly is learned for each state, or once globally for all states. For the transformation of policy output into standard deviation, soft plus and exponentially perform similarly. So most of these choices in their case appear to be relatively similar, except the ones that they point out. The recommendation here is initialize the last policy layer with 100 times smaller weights. Use soft plus to transform network output into action standard deviation, and add a negative offset to its input to decrease the initial standard deviation of actions. Tune if this offset is possible. Use tan H as both the activation function, if the networks are not too deep, right here. This is probably where the ReLUs would start to shine, and transform these samples from the normal distribution to the bounded action space. And to transform using a tan H. Use a wide value MLP, no layers shared with the policy, but tune the policy width. It might need to be narrower than the value MLP. Now this no layers shared with the policy, this might be now a result that the policy is quite brittle. So if you can detach the value and the policy, that might be of advantage. Which is also surprising, right? You would think that these two networks, if they have shared layers, they would learn more about the environment, but apparently not. Then normalization and clipping. So you get a bunch of normalization and clipping techniques, which is, for example, observation normalization. Basically means that whatever comes in, you normalize it to a given range. So that's usually you do that for supervised learning, like if you have MNIST digits. So this is a mostly black image with, can I draw on this? With like a small portion of it is white. And what you want, this is usually in the range of 0 to 255. So you have 0 to 255. What you want to do is you want to normalize that such that it's in the range -1 to 1. Or alternatively, such that its mean is 0 and its standard deviation is about 1. So people use both things, and this alone tends to already boost the performance. So the fact that this is non-negative, and also the fact that this number is somewhat higher than sort of in the 0-1 range, these are quite important, and they're going to figure out that this is also important right here. So the recommendation is always use observation normalization and check if value function normalization improves performance. So for value function normalization, I believe you would normalize the output of the value function. So instead of the value function telling you this is how much worth something is, it simply can tell you sort of that it's more or less worth than something else in a normalized range. Gradient clipping might slightly help, but is of secondary importance. Okay, cool. Yeah, so all the other things also don't seem to matter too much, like per mini batch advantage normalization and gradient observation clipping. Yep. Then advantage estimation. So advantage estimation in reinforcement learning is basically the value network needs to be trained, right? So you take a step and a step and a step and a step, and in each step you get a reward, and you perform many steps. Now the value network sitting right here needs to be trained to predict the total reward that you can get from here on until the end of the episode. Now usually what you do is you can bootstrap this by sort of a temporal difference thing, in that you consider you consider a few steps into the future, and then you ask your own value network what it thinks of the rest of the episode. Right? So basically you don't train on the entire rest of the episode, you train on the difference between this and this. And then you can get way more complicated, where you actually ask your value network at each step what it thinks, and then you go to that value network while integrating this reward, but you also go to this value network while integrating these two rewards, and so on. And then your target becomes sort of a mixture of all of these things. You can get super complex with these different variants, and they say we compare the most commonly used advantage estimators, n-step, GAE, and v-trace, and their hyperparameters. And their recommendation is use the GA with lambda equals 0.9. Okay. I feel this is not too surprising right here, because this n step is a very basic estimator, and the GA and the v-trace are better, and they say the GA and the v-trace, they appear to perform better. And they have not found a significant performance difference between the two. So cool. Last thing, no, this is second to last thing, almost last thing. Training setup. Now I believe this becomes more important. So they investigate choices related to data collection and mini batch handling. So the number of parallel environments, the number of transitions gathered in each iteration, the number of passes over the data, and so on. So this is going to matter quite a bit. The recommendation is to go over experience multiple times. So what you do in these environments is always you have a phase where you collect experience, and then you have a phase where you learn from this experience. And so you collect experience, you start from here, you collect a bunch of experience, you put all of that experience into a buffer, which is like a database. And then you have these, what they're called traces, right? So all of these are now episodes that your agent took. Now all of these episodes consists of many, many steps that the agent took. So here is one step, here is one step, here is one step. And each of these steps are going to be one training sample. So each of these steps, and also here and here, are going to be one training sample. There are multiple problems here. The first and obvious one is if you just leave them in order, then you'll have very, very correlated mini batches, and that's not good. So you want to kind of shuffle them around in here each time before you go to them. You can go through them multiple times in different order, and that works really well. They say you should go over your experience multiple times, since that doesn't hurt you and it alleviates you from the necessity to collect more data. The second thing they say is you should shuffle individual transitions before assigning them to mini batches. Okay, we've concluded that. And you should recompute advantages once per data pass. Now, what's the point here? Before we talked about you have these advantage estimators, which basically means you have to look for each step. You have to look ahead a couple of steps, decide what the value of this state is, or the advantage. And in order to do that, as we have seen, you kind of look at your own estimation of that future value. So you have this value is dependent on your own estimation of the future value. Now, of course, if you can only do this if you have these episode traces, if you have these blue episode traces still around, you know which step comes after which. You cannot do this anymore once this is all in mini batches and shuffled. So what some people do is they simply compute these things once at the beginning with the value network they have, and then they go multiple times over this data, and they might shuffle each time, but they keep these estimates. And that, of course, is more and more out of date the more often you go over the data. So what they recommend is you should always go back to this data set, recompute these estimates with your current value network, then do the whole shuffling thing again, and then do another epoch, and then basically come back to here again and recompute the advantages. It makes a lot of sense, right? But they also find that this actually makes a difference. For faster wall clock time training, use many parallel environments and increase the batch size. Both might hurt the sample complexity, but they get you a faster wall clock time, which makes sense, right? If you have more environments, then you're going to collect more experience and more different experience, and that will speed up the time that you need for learning. You might collect more samples though, so it will also increase your flops. Tune the number of transitions in each iteration if possible. Okay. So next thing is time step handling. What do they do? The choice is related to the handling of time steps. So this is the discount factor, frame skip. So in these environments, you can choose to ignore intermediate frames, how episode termination due to time step limit are handled. And their main thing here is that the discount factor is one of the most important hyperparameters and should be tuned per environment. And to start with a 0.99 discount factor. Try frame skip if possible. There's no need to handle environments step limits in a special way for large step limits. Okay, so the discount factor, which is also unsurprising, right? Because the discount factor is basically how much you discount future reward. And that is inherently dependent on the reward structure of the environment itself. So it's really unsurprising that this is an important hyperparameter, but it's good to note. And then second to last thing, optimizers. They investigate different optimizers. We investigate 2 gradient-based optimizers, Adam and RMS prop, as well as their hyperparameters. And their result says you should use Adam with momentum, though I think they found that RMS prop isn't too much behind that. But they say you should tune the learning rate absolutely, which is also known in the community, right? If you have a different problem, it might require a different learning rate, and they find the learning rate to be an important parameter for these problems. So you should tune it. But the other parameters of these algorithms aren't too much of an influence, at least on these particular problems. And then the last thing is regularization. So in regularization, they try different regularizing methods, such as entropy regularization, soft constrained entropy should not be lower than some threshold, Callback-Leibler divergence between a reference distribution, and so on. And they say, we did not find evidence that any of the investigated regularizers helps significantly on our environments, with the exception of half-cheton, which all constraints help. So they don't find a particular thing. But remember, this again, for example here, entropy regularization is used in the Impala paper, which proposes V-trace. Now they here only have an experiment where they change the loss to V-trace without entropy regularization, and in this case they turn entropy regularization on with the PPO loss, as far as I understand the paper. And there you can already see that there is a space that is not explored, that is the setting of the original paper that introduced the thing. And I think this if you can remember this study like, are all GANs created equal? They concluded that probably all GANs are created equal, especially like Wasserstein GAN isn't too much better than anything else. And the author of the Wasserstein GAN paper was furious because they clearly said in the Wasserstein GAN paper that the atom optimizer doesn't work and they had to use RMS prop, and then the RMS prop was not in that study included. So it seems that the limitations of being able to really densely explore these choices is quite hurtful in that you can only, even though this is a super large scale study and they trained so much, right? You can only ever make very, very, very limited sort of conclusions in these things. And I would say, if you are in these types of problems, definitely consider their default settings. Otherwise, what I'd much rather do is to just go to like a piece of code that implements as close an environment as possible to the one I want and take the hyperparameters from there. In the appendix here, they describe all of the things that they've tried with the choices of hyperparameters and all of the results. And you zoom in on like a random one, you already see that the results oftentimes are very diverse, very wonky, very much like, maybe, this thing isn't so relevant, or there's large performance differences that are unclear between the environments. So it remains to be seen, but the main interpretation here is that you're probably going to have to tune hyperparameters for a while on your own environments. All right, yeah, the appendix is really long, and if you want details, I invite you to look at it. And apart from that, I'll see you next time. Bye-bye.